In this video, we'll be discussing London dispersion forces. Now, we're all familiar with intermolecular forces and intermolecular attraction, the strongest of which is ion-ion, but that's not really intermolecular, is it? It's just the electrostatic force that attracts individual ions. We have ion dipole, still not exactly intermolecular, but finally we get to our dipole-dipole attractive forces, which includes hydrogen bonding. And then finally, dispersion forces, sometimes called London dispersion forces, and sometimes they're called van der Waals forces. Now, why do we need to talk about London dispersion forces? Well, we all know that the condensed phase, liquids and solids, is possible because of the attractive forces between molecules. If they didn't attract each other, they wouldn't stick to each other and form liquids and solids. We know how this works with polar molecules. Dipole-dipole interaction is caused by a polar covalent bond where the electrons spend more time on one atom than the other. The molecule looks like a small magnet, and it's this force that is analogous to a magnet that allows the molecules to stick to each other. But what about our non-polar molecules, and say our atoms? How do they stick to each other? Well, just because they're non-polar doesn't mean they exhibit attractive forces. And we know that they have to eventually attract each other because they do have melting points and boiling points. Extremely low, but they do occur. So how does this happen? Well, this occurs through dispersion forces. What happens when a non-polar atom or non-polar molecule comes up against another non-polar molecule or atom? The electrons push each other away, and we induce temporary dipoles. Once we have an induced dipole, it's going to now stick to another atom or molecule that has also induced a dipole. Now, these are extremely weak, but they do occur. They occur in all covalent molecules. However, we don't really think of them when it comes to molecules that already experience dipole-dipole attractive forces, because these forces are so much stronger than dispersion forces. But for nonpolar molecules, these dispersion forces are very important. This is the only way that we can get helium to eventually condense. We have to get it very cold, but we can get it to condense. So let's take a look at dispersion forces present in different halogens, for example. All of these halogens, they are nonpolar, but they have different boiling points. Now, if we look at this chart, we notice that there's a trend, that as the molecular mass increases, so does the boiling point. Well, why is that? Is it just because of molecular mass? Well, that's a good guideline, but if we go back to another portion of chemistry, we realize that as we go down the periodic table, from fluorine, chlorine, bromine to iodine, and so forth, atoms get bigger. So if each one of these molecules is diatomic, it just contains two of the same atom, then the molecules are going to get bigger. Bigger the molecule, the more area you have to induce a dipole and then therefore induce London dispersion forces. Same thing when it comes to noble gases. As we go down the periodic table, we see that the noble gases get bigger. The bigger the atom, the more area you have to induce a dipole, and therefore more London dispersion forces, more attractive forces, and as we see here on the right, the boiling points are going to go up. And what about more complicated nonpolar molecules? Here we have hydrocarbons. The carbon-hydrogen bond, which we don't really show it here, but at each one of these points we have enough hydrogens to form an octet around each carbon. The carbon-hydrogen bond is slightly polar, but not enough to really be significant. Plus, due to the shape of each one of these molecules, those tiny dipoles cancel each other out, and this is essentially a nonpolar molecule. Now, as we have more and more carbons and hydrogens, as we go from a 7-chain hydrocarbon all the way to a 10-chain hydrocarbon, we notice the boiling points are going up. Why is that? Well, the longer the chain, the more surface area we have. The more surface area, the more London dispersion attractive forces we're going to have. Now we have to be careful, just because that the molecular weights are going up, again, we're talking about surface area, not just the weight of the molecule that increases with increasing London dispersion forces. A good example here is, let's take a look at the boiling points of pentane. There are several different forms of pentane. Here's 3 of them. Depending on how these hydrocarbons branch, we're going to get a lot more surface area, for instance, over here in pentane, rather than all the way over here, neopentane. Now, depending on the branching that we get with the hydrocarbon, we're going to get a lot more surface area. If we have no branching, if we just have a straight chain, we're going to have a lot more surface area, a lot more attractive forces, and for example here, with N-pentane all the way on the left, we have a much higher boiling point. So just to recap, London dispersion forces are caused by induced dipoles. They're the weakest of all intermolecular forces. They're the only force present in nonpolar atoms and molecules. They're present in all molecules regardless of other forces. And their magnitude increase with size and surface area.